Hi, welcome to this video on linear programming. This video will be the first of many in the topic of duality in linear programming. So duality is a pretty fundamental cornerstone topic in the theory of linear programming, and so we're going to be spending a fair amount of time on this topic overall. But in this first video on the topic, we're just going to be talking about what the dual of a linear program even is. So where does it come from? What does it mean? What does it do for us? And specifically, we're going to derive the dual of a linear program when that linear program is in standard equality form. So really, in order to start this topic, all we really need to know is what a linear program is and what it means to be in standard equality form and the associated terminology with that. So what we're going to have when we're in standard equality form, what that means is that we're maximizing an objective function, C transpose X. And it'll be subject to the constraints, matrix equality constraints, AX equals B, and variable non-negativity constraints, X greater than or equal to 0. And when these are exactly the type of constraints that appear in the constraints, and you're trying to maximize, then you say that linear program is in standard equality form, and that's abbreviated SEF. So A, C, and B are given data, and then X is a variable which you're trying to determine. So X has to satisfy the constraints, and subject to satisfying that, you're trying to find, amongst all those X's that satisfy the constraints, find one that makes C transpose X as large as possible. So A is an M by N matrix, so it's M rows and N columns. So there's a row of A for each of these equality constraints. C and X are vectors in Rn, and B is a vector in Rm, and that's because it's the right-hand side of this matrix equality constraint, and for every row of the matrix there's a constraint, and so the right-hand side there has to be a component for each constraint as well. So there's M rows, there's M constraints, there's M components of B. We also assume that the rows of A are linearly independent, because otherwise, if they weren't, there'd be some sort of redundancy, and if there was a redundancy, we could have just gotten rid of that in the first place. So we might as well just assume that the rows of A are linearly independent vectors. So what is the dual doing for us? The point of all this is that we're going to be trying to establish an upper bound on the objective function, C transpose X. We're trying to make this as large as possible. So if we can find a value which is guaranteed that C transpose X will not surpass, regardless of what X is, well, then that would be an upper bound, and that's what we're trying to find by the dual. So let me show you how that is actually done. So we start with the system AX equals B. And what we're going to do is we're going to take a linear combination of the constraints here of AX equals B. So in practice, that works out to taking a linear combination of the rows of the matrix A, since there's one row for each of the constraints. So algebraically, what that means is that we're multiplying on the left by a vector y. So we'll have y transpose AX equals y transpose B. So I've multiplied on the left by y transpose, and y is a vector in Rm. So that's the number of components of the vector y corresponding to the number of constraints that we have coming from the AX equals B system. Okay, now why we're doing this is because, well, take a look at this. I've just put parentheses on the y transpose A part, and this is going to establish an upper bound because you can look at the format of this. Y transpose A is a row vector, and that row vector is multiplied by x here on the left-hand side of this equation. So that is of the same format as the objective function. We have a row vector, C transpose, times by x, and that gives us the objective function. So if y transpose A is larger than C transpose, then ideally that means that this overall value, y transpose AX, is larger than the objective function. Okay, so let me just write that down. If y transpose A is greater than or equal to C transpose, then we can establish an upper bound. Then y transpose AX will be less than or equal to, then C transpose X will be less than or equal to y transpose AX. And that is equal to y transpose B. So this equality is just coming from the fact that AX equals B, so then y transpose AX equals y transpose B. The inequality is just a bit more subtle. So first of all, it does need to be true that y transpose A is greater than or equal to C transpose. That's the first thing that we need to be true. But that's actually not sufficient because we need x. We're multiplying by x now. It's not just y transpose A and C. We're multiplying these things by x. So we need to make sure that the x has no sign issues. It can't be negative is what we mean specifically, because if there's any components of x that are negative, then that whenever you're multiplying by a negative, that flips the sign of inequalities, and that's just going to give you some potential algebraic mishaps, and you might not be able to establish an upper bound anymore. But of course, that's what we want to do. We want to establish an upper bound. So what we need is that x is greater than or equal to 0. But that is true because we're assuming that we're in standard equality form. So the x components of the components of the vector x are all non-negative. So because x is greater than or equal to 0 and y transpose A is greater than or equal to C transpose, then we get this upper bound. So what this means is that if you can find for me a vector y such that y transpose A is greater than or equal to C transpose, then take that vector y and multiply it by b. And that value is guaranteed to be an upper bound on C transpose x, independent of what x is, provided that x satisfies the constraints ax equals b and x is greater than or equal to 0. So if x is a feasible solution, any feasible solution to the linear program, then any y that satisfies this if condition will, when you multiply it by b, be an upper bound on C transpose x. In particular, for optimal solutions of x, that will still be true. So let's just write that down. So what we're trying to do is we're finding y such that, first of all, y transpose A is greater than or equal to C transpose, because then that guarantees us this upper bound that we can find. But look at all the y's that satisfy this condition. Then we know that for each of those y's, y transpose B is an upper bound. Let's take the smallest of those upper bounds that we can, because that will give us the tightest approximation to what the value of the original optimal solution for the original linear program is. Because y transpose B is always larger than C transpose x, so let's make it as small as it can get subject to this condition so that it's very close to C transpose x, for optimal solutions of x at least. Okay, so the second thing is subject to y satisfying the first condition. The second thing is that we want to minimize y transpose B. So that's just what we said above. Now we can have a tight approximation. Now, it's not clear a priori whether this is as good of an approximation of the objective function of the original linear program that you can get or not. Maybe there's other methods that will give you upper bounds that are even better, that are even closer to the original objective function, but that's not really for us to say right now. We'll be able to answer that question later, but right now we're just saying that if we're using this method, then the best you can do is that once you find a y that satisfies y transpose A being greater than or equal to C transpose, amongst all those y's, take the one that makes y transpose B the smallest. Okay, and so just by the way, I could rewrite this first thing as saying A transpose y is greater than or equal to C. I just transpose both sides. And y transpose B, that's the same thing as B transpose y. So I'm writing them like that because if you notice, we can actually encode these conditions as a linear program itself. I'm looking for vectors y that satisfy some constraint, and then amongst all those, I'm trying to minimize some objective function. So let me write it down. We're minimizing B transpose y such that A transpose y is greater than or equal to C. This is a linear program, and it's called the dual linear program. So it's dual to the original linear program that we started with. It's important to note that this linear program is not in standard equality form for multiple reasons. We're minimizing, first of all, and these are not equality constraints here, and there's no variable non-negativity constraints. Anyways, so it's not in standard equality form, but that's not really of a concern to us right now. It's okay. We're starting with this linear program in standard equality form, and its dual is not necessarily in standard equality form, but it's still a linear program. Here's a linear objective function that we're trying to minimize, and these are all linear constraints. And this linear program, the problem of solving it will establish upper bounds on the original linear program that we started with. So B transpose of Y will always be larger than C transpose X. Okay, so the dual linear program, here it is just cleaned up. So here it is above, and now it's cleaned up. Minimize B transpose Y subject to A transpose Y being greater than or equal to C. So let's compare. Let's compare this linear program, this dual linear program, to the original linear program. And this green comment it addresses part of the comparison, which has the data in the dual linear program, that's this one on the right, comes from the original, the original linear program. I put in parentheses primal. So that's another name for this linear program. So I'll address the comment in just a moment, but let me just label these. So this is called the dual linear program, and this is called the primal linear program. That's just a fancy name for the original linear program that you start with. So you start with the primal linear program, and you can derive the dual linear program. So the data in the dual linear program, what's the data? The given data is B, A, and C. Granted, the B and the A are transposed, but nonetheless, it's B, A, and C are the given data. Y is a variable. So the given data is B, A, and C, and that's the same data that appeared in the primal linear program. C, A, and B appeared there. And if you take a look, the way that things correspond is that this vector C, originally it appeared as the coefficients in the objective function of the primal, and now it's the right-hand side components of the constraints in the dual. And the right-hand side components of the constraints in the primal became the objective function coefficients in the dual. So objective function coefficients and right-hand side component constraints flip places in primal and dual. So that's a pretty interesting pattern. And then also this matrix A just became transposed in the dual. So that's the correspondence of the data. Okay, and again, what is the purpose of the dual? The point is that in this dual linear program here, any and all feasible solutions of the dual linear program are going to be upper bounds on the optimal solution of the primal. So you give me any vector y that satisfies these constraints, and then when I plug it into this objective function, B transpose y, it's guaranteed that B transpose y will be an upper bound on the optimal solution of this linear program. So it'll be larger than C transpose X. Okay. Let's take a look at an example. So that was a bit high level, hopefully not too much, but we can make it more concrete with a very concrete example. So here I've just picked out something with very easy to remember coefficients. So we're maximizing 10x1 plus 20x2 plus 30x3 plus 40x4 subject to the coefficients here are 1, 2, 3, 4 times the x's equals 12, and 5, 6, 7, 8 times the x's equals 144, the second one, which is 12 squared. And then x, each of the components of x are non-negative. So this is in standard equality form then, which is good, because that's all we know how to take the dual of right now, is things in standard equality form. So we have matrix equality constraints. So the matrix is the first row is 1, 2, 3, 4, and the second row is 5, 6, 7, 8 times the x equals the right-hand side, and then the variable non-negativity. So that's what it means to be in standard equality form. And if you notice, we can do two things. First, we can go through the logic of how we derive the dual, which we will do in just a moment. But we could also write down mechanically what the dual linear program is, because we just have right here, we have a concrete, I know the data of the original, so now I can write down the dual linear program in terms of the data from the primal. So we can just write it down right out of the gate. So I'll do that quickly, but you don't have to understand where this is coming from. I mean, you do. It's just you don't need to be as quick with it as I am, mainly because I'm used to this already. But what we're trying to do is minimize 12y1 plus 144y2. That's because, so 12 and 144, they were originally right-hand side components of the primal. Now they become objective function coefficients, and such that the constraints are, let me just write this as matrix constraints. So in matrix multiplication form. So the matrix gets transposed. So 1, 2, 3, 4, now down a column, and 5, 6, 7, 8. That times the vector y, where by the vector y I mean the thing with components y1 and y2, that is greater than or equal to the, now the right-hand side components, they come from the coefficients of the primal objective function. So 10, 20, 30, 40. Just like that. And so this is the dual linear program. Okay, and so we can do that every time. We can just mechanically write down what the dual linear program is, and now we know that any linear program that satisfies, sorry, not any linear program, any vector y that satisfies the constraints of this linear program, when you plug it into this objective function, that value will be an upper bound on the optimal value of this linear program. And it's not even clear, by the way, that this linear program has any solutions at all. Maybe it's just not a feasible linear program, but either it has no solutions, or it has an optimal solution, or it's unbounded. One of those three things is certainly true, and if it's bounded in one of those first two cases, then this will establish an upper bound. Okay, but let's go through the logic of how we get this dual linear program. And it's the same logic that we just went through above in the general form, but now we're just doing it for this example. So what did we say we did there? Well, what we're doing is we're taking a linear combination of the constraints. Okay, so y1 and y2 is what we multiply these constraints by. So y is a two-component vector here, consisting of y1 and y2, and so there's two components corresponding to the two equality constraints that we have in this primal linear program. And so we're taking a linear combination, and so we have y1 times, the left-hand side is 1x1 plus 2x2 plus 3x3 plus 4x4 plus y2 times 5x1 plus 6x2 plus 7x3 plus 8x4. Now, on the one hand, we know that this is going to be equal to 12y1 plus 144y2. And that's because this part with the x's, we know that by this constraint here is equal to 12. So I just replace this with 12. And similarly, the second part is equal to 144. And the idea is that this is going to become an upper bound for us. So this thing, which is also this thing, is an upper bound. So how will that happen? Well, we want to show that this is larger than, for an appropriate choice of y, that this is larger than the objective function, 10x1 plus 20x2, etc. Now, it's not clear how to do that right out of the gate, because right now this is a linear combination of y's, whereas the objective function is a linear combination of x's. So I want to write this as a linear combination of x's. So what we're going to do, in other words, is distribute the y's to the inside and factor the x's to the outside. So let's do that. So this is equal to, well, what things have a factor of x1 associated with them? You can see that when you multiply the y's inside, we'll have y1 times 1, that'll have a factor of x1, and y2 times 5, that will also have a factor of x1. So we'll have 1y1 plus 5y2. Those are the things that have a factor of x1. Now next, how about the things with a factor of x2? See, there's nothing else with the factor of x1. Everything else is x2, 3, or 4. The things with the factor of x2, though, that'll be 2 times y1, and then y2 will be times by 6. Those two things will have a factor of x2. So this will be plus 2y1 plus 6y2. And that's multiplied by x2. Those are the things with a factor of x2. And you probably see how this works by now. The next one, the things with a factor of x3, it'll be 3 times y1 and 7 times y2. You add those together, and those things have a factor of x3. So 3y1 plus 7y2 times x3, and finally plus 4y1 plus 8y2 times x4. And what we want is for, because now this is a linear combination of x's, and so the coefficients that appear in front of the x's, we want these things to be larger than the coefficients in the objective function. So here's the thing that appears in front of x1, and 10 is the coefficient in front of x1 in the objective function, so we want this term to be greater than or equal to 10. And similarly, we want this term to be greater than or equal to 20, this to be greater than or equal to 30, and this to be greater than or equal to 40. And that suffices because the x1, 2, 3, and 4 are all non-negative, as you can see above, because we're in standard equality form. So, so we won't have any sign errors. So, so then overall, this entire thing will be larger than the objective function. Okay, so we're saying, I'm not saying this can happen, I'm just saying if 1y1 plus 5y2 is greater than or equal to 10, and 2y1 plus 6y2 is greater than or equal to 20, 3y1 plus 7y2 is greater than or equal to 30, and 4y1 plus 8y2 is greater than or equal to 40. If those things are true, that's what we just said above, then what that means is that the objective function 10x1 plus 20x2 plus 30x3 plus 40x4 will have an upper bound of this thing that we just wrote down above. So this quantity will genuinely be an upper bound. And we know that that's equal to 12y1 plus 144y2. Okay? So 12y1 plus 144y2, provided that y satisfies these conditions, this thing will be an upper bound for the objective function. So we can encode this as a linear program because we're trying to minimize that upper bound to be as small as it can, so 12y1 plus 144y2, such that these constraints above hold. So I'm not going to write them down again. Let me just see if I can do a quick copy-paste here. So copy that and paste it there. Okay, great. So it'd be nice if this moved up maybe just a bit. So maybe right there. And so this is the dual linear program. And you can see that this matches exactly with what we just mechanically wrote down from above. So we can derive it, using some logical deduction, or we can just mechanically do it because we've already done the logical deduction in the abstract. But here it is, and this is the dual linear program. So any y that satisfies these conditions means that this will be an upper bound, and we're trying to minimize that upper bound. And here it is again. So so if I can get them both in frame, I've just cleaned it up here. So this is the same thing. We're minimizing 12y1 plus 144y2 subject to those constraints. And now let's compare. Let's compare the primal linear program to the dual linear program. So I've written them now as matrix notation so that we don't keep writing the same variables over and over. So we're maximizing 10, 20, 30, 40 times x subject to the conditions 1, 2, 3, 4 times x equals 12, and 5, 6, 7, 8 times x equals 144, and x is non-negative. And then here's the dual. So let me label these again. This is the dual, and this is the primal. And we can see how the data corresponds. So originally what happens is we have 10, 20, 30, 40, which appears as the coefficients of the objective function, and in the dual it becomes the right-hand side components of the matrix constraints. So here, the right-hand side components of the matrix constraints, now they become the objective function coefficients in the dual. So they flip places. And then finally, you can see that the matrix gets transposed. So 1, 2, 3, 4 was the first row. Now it's the first column. 5, 6, 7, 8 was the first row, now it's the first, or sorry, second row, now it's the second column. And finally, we're saying y is free here. So that just means that y has no restrictions, no variable restrictions on it, other than what's imposed by these matrix constraints. And that was implicit already in the formulation above. Well, we didn't write that because we didn't write any variable constraints. That means there are none. But now we're just explicitly acknowledging that fact by writing y is free, meaning that explicitly saying there's no constraints on the variable y. That's in contrast to the situation with a primal linear program where x is not free, x has constraints associated to it, x has to be non-negative. It's part of what it means to be in standard equality form. So there you go. That's the primal linear program, and there's the dual, and there's the correspondence between them. And just for fun, real quick, we can take a vector y. So let's say, for instance, y equals 2, 4. I already know that that satisfies these constraints. I checked. So, for instance, 1 times 2 plus 5 times 4, that's 22, which is larger than 10, and that works all the way down. So what that means then, so y is feasible, so we can plug this y in to the dual linear program objective. So we have 12y1 plus 144 y2. So that's 12 times 2 plus 144 times 4. And I know ahead of time, I computed this, that's equal to 600. And so the point is that there is no way that you're going to find a solution to a feasible solution to the primal objective, to the primal linear program, such that the objective function exceeds 600. 600 is an upper bound. I'm not claiming it's the best one, because this is only a feasible solution. It's not necessarily the minimal solution, but at least it's an upper bound on this objective function of the primal. So, okay, that's roughly it now. So what did we talk about in this video? We said, first of all, we started with a linear program in standard equality form, and that's called the primal. And so I'll label that parentheses P, P for primal. And then we were able to construct the dual, and this is what the dual looks like. And I'll label this parentheses D, D for dual. And there's this correspondence of the data, so there's a deterministic way you can just automatically figure out what the dual of this linear program is. And the purpose of it was that when you found a y that satisfied these constraints that was feasible, then this linear program objective function was an upper bound for this objective function. So B transpose y would be an upper bound for C transpose x. So this would be greater than or equal to C transpose x. And that's all the features of the dual linear program that we're going to talk about for this video. So there's lots more to say about duality, the dual linear program, and what it does for us, but that'll wait for future videos. So that's it for this video. Thanks for watching.